missing side in a pair of similar figures. So in this first example, we have two triangles which are labeled with an AA similarity, right? We have the single tick mark in the left and the double tick mark in the right. And so when we do similar triangles, when we're working with similar figures in general, that means that the sides have to be proportionate inside of the two figures. So here I'm going to illustrate this with colors by going, let's see, that side 7, that's the left hand side. And over here, that side is X. And then along the bottom, we have a side length of 10 and a side length of 20. Now, it also turns out that the 5 to the 10 on the third side will also be proportionate. Actually, why don't we draw that in too, just in case you care. So we have blue, green, and red in this picture, and all the sides are proportionate, so they form the same ratios. Now, the only unknown is the blue in the big. So as I set this up, I'm going to make a ratio of small triangle to big triangle. There are alternate ways you can do this, but I like small to big because it allows me to do the same thing every single time I set this up. So as I set up my small to big, I can see that in my small triangle I have a 7 on the left, and in my big triangle I have an X on the left. Then I have in the small triangle a 10 on the bottom, and in the big triangle a 20 on the bottom. So now if we pretend, or not if we pretend, if we set 7 over x equal to 10 over 20, we can perform some cross multiplication here to yield 7 times 20, which is 140, equals x times 10, which is 10x. And so after dividing by 10, we can see that the missing side must have been x equals 14. Now if you're very observant, you might have just noticed that, well, 10 multiplied by 2 is 20, 5 multiplied by 2 is 10, so this last side must be 7 multiplied by 2, and that's where 14 came from. So that's a shortcut if the numbers are pretty. But let's try one where maybe the numbers aren't quite as pretty. Yeah, we got some decimals in this one. So as I set this one up, I notice already that in the big picture, the one on the right, the y is the unknown. So over here I'll label the corresponding side as blue, so we have this y to 7 ratio. And then I'm just going to choose whichever side I want. I'm going to choose the ones that have whole numbers because they might be easier to work with. So there's a 2 in the top right and there's a 3 in the top right. So again, going small to large or left to right, however you want to think about it, we have 2 to 3. So if we now perform cross multiplication, we can see over here that y times 3 is 3y, and over here 7 times 2 is equal to 14. So therefore, if we divide both sides, we yield y equals 14 thirds. So not nearly as nice a number, but still consistent with the idea of similar figures. So now why don't you pause the video and try the next one on your own. We did this pentagon. Why don't you try this quadrilateral with some real hideous decimals, right? Or not hideous, I mean they're just different numbers, right? So try to do this with the decimals. And if, assuming you pause the video and tried this on your own, notice that the unknown is over here with z, so we're definitely going to take the side with a 5. Choose whatever other side you want. Notice they're all decimals here, so it's not going to be like anything is easier than any other object. So I'm just going to go with this one because it's the smallest number. Hopefully the calculations will be easy to work with. So then we have a z over 5 going from the big one to the small one, the right to the left. And on the other hand, if we go right to left, we have a 2.8 over a 2. So then we perform a little bit of cross multiplication, and 2 times z is 2z, and 2.8 times 5 is 14. So therefore, if we divide both sides by 2, we end up getting a final answer of z equals to 7.